previous videos we talked about linear functionals. A linear functional is a thing which maps vectors to scalars. And we discovered that any linear functional on the space H can be obtained from the vectors of this space by operation called Hermitian conjugation. It means that for any linear functional we can find the vector phi, which Hermitian conjugate defines this functional. And we agreed to represent this functional as a vector rho with conjugated components. Now imagine that we have a functional defined by some vector phi. I'm now going to define another functional based on this bra phi and some linear operator a. My new functional, I'm going to denote it as phi a, will act like this. For any vector psi, we first apply operator a to it, and then bra phi. This new thing is indeed a linear functional. It takes vectors as its input and returns scalars. And you can easily check yourselves that its action is linear. But since it is a linear functional, there must be some vector, phi a, which Hermitian conjugate defines it. And this vector is defined by the initial vector phi and the operator a. This operation, the construction of a vector rho from another vector rho, with the help of some operator, is called the action of the operator on the left. So with any bra, which means any linear functional from the conjugate space, we can apply this operator a, like this, on the left, to construct another bra. In the matrix representation, this operation is defined much simpler. It is again the multiplication of two matrices, the vector rho, which represents our initial functional bra phi, and the matrix of operator a. When you multiply a row by a matrix, you obtain another row. This is what happens here. The action of a on the left is a matrix multiplication, where a stands on the right and its argument on the left of it. And when this bra phi a acts on some vector psi, in the matrix representation we can write it like this. Row phi multiplied by matrix A and then multiplied by column psi. Since it doesn't matter in which order we perform these operations, we are going to rewrite it in Dirac's notation as this. This thing here is called the matrix element of A, corresponding to the vectors phi and psi. This name comes from a simple observation. If instead of phi and psi you take the vectors of the orthonormal basis with all zeros except one place, I and j, for example, then this expression will give you the component of the matrix A on the row I and column j. So to compute this, we can go two ways. First apply A on the left, on phi, and then compute the scalar product of the result with psi. Or you can apply it on the right, on psi, and compute the scalar product of phi and a psi. Both ways will give you the same answer. So we are not going to place any of these parentheses anywhere in this type of expressions. Now we remember that each bra corresponds to some ket. So this bra, phi a, also corresponds to some ket, phi a. Is there a way to obtain this phi a ket from the ket phi? Again, if we reflect on this question a bit, we will notice that the ket phi a is uniquely defined by the ket phi and the operator a. In other words, we just defined a way of constructing one vector from another, vector phi a from vector phi, for example. And the way of constructing one vector from another is an operator, remember? Operators transform vectors to vectors, and it is exactly what we just did. So there must be some operator A star, which transforms vectors just the way we did with phi and phi A. And I call it A star to stress the fact that this operator is somehow connected with the operator A. The operator A star is called the adjoint operator of operator A. What can we say about the operator A star? First, we can easily prove that it's linear. Second, it is defined by the operator A alone. So there must be the way of constructing A star from A for any linear operator A. And the most interesting part is this. Since the ket phi A is the Hermitian conjugate of the bra phi A, we can write it like this. The Hermitian conjugate of A acting on the left of bra phi is A star acting on the right of phi. This allows us to define the operation of Hermitian conjugation on operators. The operation of Hermitian conjugation. First, transform complex numbers to their conjugates. Second, transforms kets to bras, which means vectors to linear functionals. Third, transforms bras to kets, which means linear functionals to vectors. And fourth, it transforms operators to their adjoints. And it is very convenient for us to notice that when we perform the operation of Hermitian conjugation on some expression, we have to do two simple things. First, substitute each element in the expression by its Hermitian conjugate, and second, rewrite all elements in the reverse order. The second rule is not strict for the scalars. It is usual to write them in the beginning of the expression. Now, when we know how the adjoint operator is defined, it would be good for us to discover how to obtain its matrix. Imagine we have some operator A, and we have its matrix. When in the previous episode we considered the action of A on some vector x, I told you that we can imagine it as a separate action of linear functionals, represented by the rows of the matrix A. Since we remember that Hermitian conjugation transforms vector rows to vector columns with conjugated components, it is exactly what we need to expect from the Hermitian conjugation of a matrix. Its rows become columns with conjugated components. So for any matrix A, its adjoint, matrix A star, is just transposed matrix A with its components conjugated. It is as simple as that. Now, when you know all that, you may notice that some operators, as well as some numbers, are neutral with respect to this Hermitian conjugation. The numbers are neutral to it if they are real, with zero imaginary part. The operators are neutral if, after transposition and conjugation of all the components, they stay the same operators. This type of operators, which are neutral with respect to Hermitian conjugation, are called self-adjoint or Hermitian operators. They are very important in quantum mechanics because they represent observables. We already talked about observables, and I told you that an observable is defined by an orthonormal basis in the state space. Now I tell you that an observable is a Hermitian operator. How's that? Let's see in the next episode.